Good afternoon, folks. How are you today? We are in week number 9. This is lecture number 25. Last week we started methods to evaluate a definite proper integral. So we are given a, b, and a function of x, and what we want is integral from a to b of this function with respect to x. And I said we are going to cover all of these methods. Last week we finished trapezoidal rule. So let's see what trapezoidal rule does. So in trapezoidal rule, here is our function. We want to evaluate the integral between a and b. So we chop up this interval in n strips of equal width h. So when we do that and number our x values starting from x1, we'll have x1 and x2 enclosing first strip. So if we go to n strip, we will be enclosing it between xn and xn plus 1. So we'll have n plus 1 points. Then each strip we approximate as a trapezoid. So if we look at the trapezoidal area, say of the ith strip is between I and I plus 1, point I and I plus 1. So we average the two function values, that's the average height of the trapezoid times the trapezoid width. So this is one strip. When we add all the strips up, you can see h by 2 is a common factor. And last week we found out that basically we have a weighted sum of function values where we give one weight to first and the last function value and 2 units of weight to all the interior values. Then we looked at our truncation error and we found out that for one strip, the truncation error was minus h cube over 12 times second derivative at some value zeta I on that ith strip. So we are saying local error, that is for one strip, is proportional to h cube. So when we sum up all the local errors, basically we are saying h cube over 12 times n times some average second derivative value. N is of course b minus a over h. So our total truncation error becomes minus 1 over 12 b minus a times second derivative at some zeta average value, which is between interval a and b, times h square. So this total error is called global error for n strips, and this is proportional to h square. So what we find in trapezoidal rule is that our global error ET, which is minus 1 over 12 b minus a times second derivative at some zeta average times h square. Now this value is a very weak function of h, usually. So for all practical purposes, we can say this is a constant. So all of this is really a constant. So we can write ET when we say is proportional to h square, we can say this is almost constant times h square. So we can utilize this idea to do a better estimation. And this better estimation is known as Richardson extrapolation. So in Richardson extrapolation, what we do is we estimate the area or the integral using a strip size h1. So obviously the strip size will have an error c times h1 square. So if we add that error, we will get our true value. Now we made an approximation here. We said this is a constant. So this may not be a constant. So we will call, instead of true value, we'll say this is a better value. Well, we could have used a different strip size, h2, which would have an error, h2 square, c times h2 square. So when we add the error, again, we'll get a better value. So now what we have is we have two equations and we have two unknowns. Our unknowns are c and a beta. So we can solve these two equations in two unknowns for a beta. So we find that a beta is equal to h1 over h2 square times area h2 minus area h1 over h1 by h2 square minus 1. So what this is really a weighted average. What we mean by that? We give h1 over h2 square weight to AH1 and we give negative 1 weight to AH2. Sorry, other way around. We give H1 over H2 square weight to AH2, but negative 1 weight to AH1. And then we did an average, right? So let's suppose our strip size were a multiple of 2. Then this equation, I'm sorry, H1 over H2 is 2. Then this equation will become A beta is 4 times AH2 minus AH1 over 4 minus 1, which is 3. So notice when we say H1 over H2 is 2, that means H1 is twice as thick and H2 is half as thin. So what we can do is, instead of remembering H1 and H2, we say we give 4 weight to area using thin strips. We give negative 1 unit of weight to thick strip area, and our total weights are 3. So the question is, how good is this estimation? So we started with trapezoidal estimate, which was proportional to, error was proportional to CH square. So now this A beta error would be proportional to some other constant, CH4. So we are going to have lower truncation error in this better estimate. So you may remember I did an example last week where I made a function table. I had x and a function of x. X was spaced zero point 0.1 apart. And our function values to 3 digits. What these values? Please work with me. Take out your calculator. And then what we did was we gave them weights. We gave them weights 1, 2, 2, 2. And then we did a weighted sum. And after we did a weighted sum, we got 24.538. Using h is equal to 0.1, we got area of 1.2269. So we multiplied this by h over 2. So now what we can do is we can increase the strip size. So we will just throw out all alternate values. Sorry, not this one, this one. Okay. And then we'll do our weighted sum. So we will have 1.000, 2.444, and so on and so forth. So let's fill up this table. 2.984, 3.646, and this is 2.226. So we total it up, and this time we'll get 12.300. So now when we use h is equal to 0.2, remember h is 0.2, right? Our area is equal to 1.2300. So what we can do is we can build a table. So we can say h.1 area by trapezoidal rule was 1.2269. When h is 0.2, it is 1.2300. So we give this 4 units of weight, we give this negative 1 unit of weight, and we will get a beta, right? So we use this formula 4 times 1.2269 minus 1.2300 over 3, and we will get 1.2259. Okay, so you may remember actual error. Our true value was 1.2255. Remember, this was integral of e to the power x. Our approximation is 1.2259. This is our a beta. So our actual error is reduced further, right? So remember, this was our best value. This was 0.0014 off. Now we have improved it by an order of magnitude. So this better value has truncation error that is proportional to h to the power 4. So this was interesting. Let's see if we can apply this repeatedly. So what we can do is we can use a process called Romberg integration. So let's suppose what we have is we have an area estimate using strip size h1. And let's suppose it has an error which is proportional to power m. So we can get A better. Let's do same thing using a strip size h2. It would have an error proportional to C times h2 to the power m. So when we add that error, we'll get A better. So again, two equations, two unknowns. We solve for A better, and we will get h1 over h2 to the power m times AH2 minus AH1 over H1 over H2 to the power m minus 1. So same idea, we are doing a weighted average. Now our errors are proportional to H1, H to the power m. So our weight factor here is the ratio of the two strip sizes to the power m. So if we assume that H1 over H2 is equal to 2, so now our formula simplifies. It becomes A better is 2 to the power m, and again we will use thin strip minus thick strip over 2 to the power m minus 1, where m is the exponent on h, m is exponent of h, error term, in A thin and A thick. So we had trapezoidal rule. When we use A thin and A thick, m was equal to 2. So now with Richardson extrapolation, we got a h to the power 4 estimate. So what we can do is we can use that 4, m is equal to 4 here, and we'll get a still better value. That still better value would have an error proportional to h to the power 6. So we can make a table. So let's make a table. Romberg integration table. So here is h. Here is using trapezoidal rule. We had 0 0.1, we had 1.2269. Then we just did 0.2, we got 1.2300. So we got an A better, proportional to h to the power 4. And we got a value using these two, 1.2259. Remember, we gave 4 units of weight here, negative 1 unit of weight here. So I'm going to flip my page, and I'm going to say, remember we had thrown all these alternate values, right? Now we throw again alternate values. So we'll throw this one, keep this one, throw this one. So now we have just two strips. These two strips are 0.4 wide, right? 0.4 wide. So we can do trapezoidal rule again. So please do that by yourself so you see what value you are getting and match mine. So two strips, trapezoidal rule. we'll get 1.2420. Now we can combine these two. Give it this 4 units of weight, give this -1 unit of weight, do Richardson extrapolation, and we'll get 1.2260. Then finally, instead of 2 strips, we can just have 1 strip. Do trapezoidal rule. Please do that on your own. Extrapolate these two values, we'll get 1.2259. So now we have a column of h to the power 4 values. So we can now give this a weight, 2 to the power 4. 2 to the power 4 is 16. Give this -1 unit of weight, so we can get even better value, proportional to h to the power 6. So we'll get 1.2259. Similarly, combine these two, 16 weight to this, -1 to this, we'll get 1.2260. So now we have two values in this column, h to the power 6. 2 to the power 6 is 64. So we can give this 64 units of weight, this -1 unit of weight, and we can get our final answer, which will have error proportional to h to the power 8. So we do this 64, -1, and we'll get 1.2259. So notice, eventually we don't improve any further because we are limited by number of digits. But this is the best answer. So as we go up, our error decreases. And as we go across, our error decreases. So this is our best answer. Okay, so we have seen trapezoidal rule. So this column was trapezoidal rule. Then we applied Richardson extrapolation to those values, and we got this. And then we built the Romberg integration table by repeatedly applying that Richardson extrapolation to get this final best value. Okay, let's look at our next method called Simpson's one-third rule. So in Simpson's one-third rule, what we are going to do is we are still going to take our range AB and we are going to divide it into n equal width strips. So 1 to n. So this is x1, this is xn plus 1. So n strips of width equal to h. So we know b minus a over h is equal to n, or b minus a over n is h. Okay. But we are going to make sure that n is an even number so that we can pair up the strips. And then what we are going to do is, if we have n strips, therefore we have n by 2 pairs. To each pair, we fit a parabola. Okay. So let's draw a pair of strips. So this is our x. This is our function of x. So let's say we are going to pick up the strip that is centered around xi plus 1. Make sure I'm numbering my points the same way. Yep. And xi plus 2. So this is function I plus 1, function I plus 2. So what we do is we fit a parabola to it. So our parabola would look like y is ax squared plus bx plus c. So instead of using ABC, since a and b are used as interval limits, I'm going to use p, q, and r. So let's go ahead and say, if I want the area under the parabola, what I want to do is I want to integrate this parabola, px squared plus qx plus r, with respect to x. And notice these x values are not particularly important. We are interested in width. So we can recenter this. We can call this 0. We can call this minus h. And we can call this plus h. So we can integrate from minus h to plus h. And this would be the area of our pair. Okay. So let's integrate this. So we'll get px cube over 3 plus qx square over 2 plus rx from minus h to plus h. So we will get ph cube over 3 minus of minus ph cube over 3. So we'll get 2 ph cube over 3. This would cancel out because the signs are reversed, and we will get 2rh. Okay, so this is the area of our pair. Now let's fit our parabola. So we know at negative h, actually at x is equal to 0, our parabola evaluates to fi plus 1. Let's take minus h first. Our parabola evaluates to fi. So we'll say fi is, we'll put in minus h. So we'll get ph square minus qh plus r. Then at 0, our function value is, so at x is equal to 0, is just r. At plus h, our function value is fi plus 2. So it'll become ph square plus qh plus r. So you can see we have 3 equations in 3 unknowns. Our 3 unknowns are p, q, and r. So we can solve for them. So we will find out that p is equal to yi, or fi, really in our case, fi minus 2fi plus 1 plus fi plus 2 over 2h square. Q we will find out is fi plus 2 minus fi over 2h. And r you just found out was Fi plus 1. Okay, so we substitute all this PQ and R into our area of the pair. So we will get area of the pair is H over 3 times Fi plus 4 Fi plus 1 plus Fi plus 2. So the name 1/3 rule comes from this H over 3 factor. Also notice for a pair of strips, our weights are 1, 4, 1. So now if we want to total up all the pairs, H over 3 is a common factor. For the first pair, we'll write F1 plus 4F2 plus F3. For the second pair, we are going to write F3 plus 4F4 plus F5. On and on and on. For the last pair, we are going to write Fn minus 1 plus 4Fn plus 4Fn plus 1. Oh, no, not 4, 1, just 1. Right? So one very interesting thing we see again is that the first function value and the last function value appears only once. The even numbered function values inside all have a weight of 4. Odd number values appear twice, have a weight of 2. So we can write our formula. A total is H over 3, first function value, 4 times all even numbered function values inside, 2 times all odd numbered function values inside, and then of course the last function value. So it appears again we have H over 3 factor, and then we have the weighted sum. And our weight for the function sum are 1, 4, 2, 4, 2, on and on like that to 2, 4, 1. So this is our weighting scheme for Simpson's 1/3 rule. So let's go ahead and do our example again. So this is x, this is function of x, spaced 0.1 apart. I'm going to copy down the values again. Again, my suggestion to you is do it with me. Take out your calculator, write this table yourself. Because you'll be doing similar thing on your quizzes and tests. Okay. So our weights are 1, 4, 2, 4, 2, 4, 2, 4, and last one is 1 again. So we do a weighted sum. Okay. So it's in my table here. Let's do 1.000. I'll show another one, 4.424. Next one is 2.444. On and on and on. Last one is 2.226. So we total them up, we get 36.776. So our area is H over 3. Remember, H is 0.1. 0.1 over 3 times this 36.776. So we will get 1.2259. Okay, notice this is the same value that we got in our Romberg integration table. So we got 1.2259 here when truncation error was h to the power 4. So this is what we are going to find in terms of error. So I'm not going to derive this time the error, but in Simpson's 1/3 rule, our local error, that means just for one pair of strips, is minus 1 over 90 fourth derivative at some zeta, which is on that pair of strips, times h to the power 5. So when we multiply this by n by 2, because remember we have n by 2 pairs of strips, we will get global error, which is all n strips. Remember, n by 2 pairs. So we'll get minus 1 over 180 times b minus a times fourth derivative at some zeta average times h to the power 4. So the key idea here is that our truncation error is proportional to h to the power 4. So let's see what happens. We calculate actual error. So we got 1.2255 was our true value. 1.2259 we just got as our approximation. So our actual error is 0.0004. Let's calculate our error bound using this formula. So 1 over 180 b minus a fourth derivative. Remember, if our function is e to the power x, all the derivatives are e to the power x, and they are maximum at maximum x value. So the maximum fourth derivative value would be 0.8 times 0.1 to the power 4. So we will get 10 to the minus 6. And this should be more than that. Error bound should always be more than the error. What happened? How can our error bound be less than the actual error? Well, it turns out that we don't have enough significant digits, sufficient digits in our table of function values. So our original table had only 4 significant digits in each value. So how can we expect that our result should have more than 3 correct decimal digits, right? Now, if our original data, in this place, I have kept 7 decimal digits. So if I have 7 decimal digits, I do my weighted sum, I do my h over 3, and I get this as our new value. So now we calculate what our error is. So when h is equal to 0.1 and I keep 7 decimal digits, I get area by Simpson's rule. You just saw it in the previous slide. we get 1.2255417. That's 7 digits. And of course, our true value is 1.2255409. So our actual error, which is the difference between these two values, will be 0.8 times 10 to the minus 6. Whereas our error bound, we just calculated, remember, is 1 times 10 to the minus 6. So obviously error bound is larger than actual error, which makes sense. Okay. So you can see our truncation error goes down if we decrease strip size. Truncation error goes down. Right? But when we decrease strip size, we have more strips. That means we do many more calculations. And if we do many more calculation, round off error goes up. Let's write this in the reverse way. Suppose we increase h, then our truncation error would increase, but our round off error would decrease. So if we plot this qualitatively, so when h increases, truncation error increases. So truncation error increases. But round off error decreases. We are interested in total error. So total error curve might look like this, ET plus ER. So obviously there is some optimum strip size. Okay. If we choose a strip size larger, then truncation error takes over. If we choose strip size smaller, then round off error takes over. So we have to be careful. We don't use too few strips or too many strips. Too few strips, truncation error becomes large. Too many strips, round off error becomes large. So remember that.